you. Thank you for coming back. So today I will finish what we did. Well, there was a little bit that I didn't have the time to do yesterday, and then I will move into a different subject. I'm trying to make the point that the Hamiltonian action is very important, and it has many nice properties, but also the Lagrangian action also has very nice properties, and it's also very important. I'm just really trying to make the point that they're both equally relevant, equally useful. In some things, one might be the right way to do it, and in others, the other one. And I think the best is that you have to master both. You have to really understand how the Hamiltonian mechanics work and how the Lagrangian mechanics works. And then you will be able to tell, which one to use in this problem or this other problem. So, yesterday was more about the Hamiltonian action. Today will be more about the Lagrangian action. I will show you some nice properties of the Lagrangian action, and then try to convince you that the best you can have, the best work, if you really master both of them. Okay, so the calculation that I wanted to do is to prove. This is something that you can do with the Hamiltonian and not with the Lagrangian. And I will do it in the simplest case, and then it's a very simple exercise to do it in the general case, but it's quite long. So given an action, so this is a Hamiltonian action, so it has some coordinates QA, some momenta, Lagrange multipliers on the alpha, and this one, the A. So I will consider this case in which there's no Hamiltonian, no non-zero Hamiltonian. So this is not like QED or electrodynamics. It does have a non-zero Hamiltonian that I call it H0 yesterday. H0 carries the energy density, which exists for electrodynamics, but it doesn't exist for gravity, for example. So this example includes gravity, and it includes all the theories which have invariance and the changes of coordinates. In that case, you will never have, for example, change sign of theories or all gravitational theory, FR, whatever gravitational theory you might have where the metric is a Hamiltonian field, with a variable with respect to the metric, will have this form. We will have some momenta, some Qs. Many of them, if this is a field theory, this index A runs over the space, plus 1, 2, 3, 4, whatever fields you might have. And then you will have some set of constraints, which will be many of them. If you have a field theory, of course, this will be a density of constraints and some Lagrange multiplier. Okay, so these indices run under, it will be infinite values or a finite number of values. The important point is, as I said, general relativity falls in this class. So general relativity is inside this class, and all gravitational theories. Chern-Simons theories don't have a metric, they don't depend on a metric, but yet they have invariance and the changes of coordinates. And again, the Chern-Simons action can be written in this way, with some momenta, coordinate momenta, and some constraints, and some Lagrange multiplier. So this is a really, really wide class of theories. And what we're going to prove is that if the constraints are first class in the sense that we defined yesterday, then there's a yes. Let's do the calculation, because it's a very easy calculation, and then you're in one go, you're doing the calculation for all possible theories, pretty much. Well, not all of them, because as I said, you have many theories. If you have a mill theory, you have to include a non-zero Hamiltonian, okay? And the same with electrodynamics and many other examples. But the calculation is again very easy, but I will do it in the simplest case. Okay, so given an action with a property, that the Poisson bracket So this is this function depends on the p's and the q's. So the Poisson bracket is well defined. It's the derivative of the p with the q's, but this is anti-symmetric combination. And these are called the structure constants. And then there's some constants. They can even be functions. It's not too relevant. I mean, there's some regularity conditions you need to impose here. But let's leave that aside. And let's assume they're constants, which is the most normal case. But it's not always the case. For general relativity, for example, these are not constant. They depend on the metric. But that's the point is that the Poisson bracket closes. So you take the Poisson bracket of two of them, and then you get another constant. Okay, so now so the claim, the action is invariant so this is what we're going to prove. Now this Poisson where epsilon this is the crucial aspect of this transformation, that the parameter, this is the parameter of the transformation, which is supposed to be very small, is infinitesimal, is a completely arbitrary function of one. There's no restrictions on the parameter at all. That's the main difference between a gauge symmetry and a net sphere symmetry. For net symmetries, these parameters normally have either constants or depend. They could depend on time, but depend in a prescribed way. Like it could be the constant times p, for example. But it's not an arbitrary function of p. Remember always the Nether theorem, what we proved yesterday. The Nether equation has this form. So if the parameter depends in some prescribed way in terms of time, then well, that will give you a combination which is constant, and then that will give you conditions on the charge Q. But if epsilon is completely arbitrary, it's a completely generic function of t, and then you have this equation, the only solution for this equation is Q equals 0. And then this gives exactly the constraint. You can work out that. We can work it out backwards when we finish this calculation. Okay, so this is just a notation. The Poisson bracket. This would be the derivative of phi with respect to p. A times alpha. This one would be Q minus sign. So the Poisson bracket is just a notation. It's a very useful combination, but you don't have to get confused with, what is this object? So what I'm saying is that if I transform Q in this way, with the radiation of phi with respect to p times parameter, and p is minus the radiation with respect to q times the parameter, and the Lagrange multiplier, which is also variable, the Lagrange multiplier is not fixed. It's another variable in the action. We'll have to transform it this way. This is, by the way, this is the dot. If you remember yesterday, when we wrote the action for electrodynamics, the constraint appeared, it had this form, and it had the Lagrange multiplier for electrodynamics was the time components of the gauge field. And this is the Lagrange multiplier. And the gauge transformation from A, this is what I mentioned yesterday, is the mu, and delta A0 is precisely, let me use the same notation, lambda dot. So the Lagrange multipliers always transform with the time derivative of the parameter plus something that has to do with the structure of the algebra. This piece, of course, has to do with this structure constant here. But then the main, well, I don't try to say that this is more important than that one. Just say that the fact that the time derivative of the parameters appear on that transformation comes already, and it's something you already can see in the electrodynamics. Okay, so let's prove this because it's so easy. Now, let me, one thing. I never remember the exact coefficient. I think there's a minus sign here, but I will put a exclamation sign here because we'll have to find the correct factors. There might be a minus sign, a factor of 2 or something. Okay, but we will work it out, and then we can. I'm just saying that the coefficient here might be slightly different than what I wrote over there. Okay, so let's get to work. I have to consider the variation of the action. So I will have the variation of the A and Q dot plus the A, the variation of Q plus the alpha minus, and here I will write lambda alpha, so I will write immediately the derivative with respect to the P's, delta PA plus this alpha here. So that is the variation of the action. Okay, just varying everything that moves. In particular, the Lagrange multipliers. And then another crucial sentence, which I repeated yesterday a few times, when you prove invariance of an action, you don't use the equation of motion. You don't use any equation. You don't use the constraint. You don't use the Lagrange equation. Nothing. You have to be able to prove that this is a total derivative without using any equation. The only thing you are allowed to use are the transformations. So the transformations are given over there, and that's the only thing you know, which gives you the value of the variation of P, which is a function of P, the variation of Q, and the variation of lambda. And that's all you have to apply it, and then prove that this is a total derivative without using the constraint or without using. I mean, don't even think that but you find alpha is equal to 0, so this will not contribute. No, because if you do that, you're proving nothing. Let me just maybe stop 1 second on that. If you use the equation of motion, then any transformation is a symmetry. A symmetry, remember that. A symmetry is a transformation that leaves the action invariant up to a boundary return. If you allow me to use the equation of motion, then I can prove you that whatever transformation you have will be a symmetry. Why? By definition, because the variation of the Lagrangian is always the equation of motion plus the variation with respect to typically something like this. This is by definition of the only Lagrange equations. You pick up the equation of motion plus a boundary term. And this is the variation of the Lagrangian. So if I use the equation of motion, well, I will get a boundary term by definition. Okay? So that's the difference between a symmetry and finding the equation of motion. I need to be able to prove that this whole thing is a total derivative without using any equation, just the transformation. Okay, so let's practice transformations. Before that, I will do, this is a function of t. Remember, delta q is not an operation. It's not like delta applying over q. No, delta q is a function of time. Okay, so I can always put a minus sign here and put it over there. Plus a boundary term. A symmetry, it would be a symmetry if the variation is up to a boundary term. So I can just forget about the boundary term. This will be the same. Okay? Now, after doing that, then I compute delta p. Delta p is over there, is minus the variation with respect to q. Sorry, this is a here. K, A times the parameter minus B dot A, and the variation of this one please correct me if I do a mistake, because then I have minus the alpha minus alpha, and here what do I have? A delta P. Where did I put the minus sign? In delta P. So then it will be minus. And I will have to use beta. 2A. Beta. And delta Q is I hope I have it not. It might be. Well, everything looks all right. Okay. So this is just plugging the transformations, which are these functions over there. And remember, delta P, delta Q, they're just functions of time. It's not. In some books, there's this discussion whether d and dt commute with delta or not. This is just not necessary. If any of you get confused with that, please knock at my door and we can discuss it. But it's you just treat delta P as a function. And the derivative of a function is just the derivative of a function. There's no distinction between taking derivatives or taking the derivative. Okay, so now here, what do I have? I have epsilon alpha, but you see what I get? The variation with respect to Q times Q dot, the variation with respect to P times P dot. This is exactly the total derivative of phi alpha. That's the derivative with respect to one, this function. With respect to P plus the other one. So these two terms collapse in this one over here. Now I still have the alpha, the alpha. And here, if you're looking from far away, you might have already noticed that this is exactly the Poisson bracket of phi with itself. So I will write it in this way. This is exactly phi alpha and beta and epsilon beta. Don't confuse the Lagrange multiplier, which is lambda, with the parameter of the transformation, which is epsilon. The two very different concepts. The Lagrange multiplier is a variable in the action, something like a variable with respect to it. While the parameter of the transformation is just a number you put there, which is like the angle, how strong the transformation is. Okay, so now we do two more things. One integral, I will do an integral by parts here, another one, and then I will get rid of the boundary term. I will pick up here. I will call it now epsilon dot. This term. I have now delta alpha phi alpha. And here, I use the condition that the constraint form a closed algebra. Because this just pick up exactly the Poisson bracket. So then I have gamma alpha beta phi gamma. And epsilon beta. Let me do a line here. So the crucial thing here is that what I have is that everything, I have the constraint. So I can factorize the constraint. And I will use this gamma, and I will have minus epsilon gamma.
Max, I think the sign of the first term is the opposite. The sign of the first term is the opposite.
I did an integral by parts here.
Before.
Sorry, there was a sign here. Okay, sorry. Thank you. Is that right? Yeah. Okay. Yes. I will use the index gamma minus delta gamma minus gamma alpha beta But there might be some signs, please. You can work out all the signs in great detail. But basically, so there's some signs there to be fixed. Okay, so it's a homework for you to work this out with great detail and then fix all the signs. It's just up to signs. But with this transformation of delta, then this is equal to 0. So up to boundary terms, because I did two integral by parts. So up to boundary terms, when I plug that transformation into the direction, it gets 0. So, exercise, well, fix all the little signs here, it's just a bit of convention. The other homework is to repeat this exercise if you have a non-zero Hamiltonian. But again, the exercise will be exactly the same, But you have to, if you have a non-zero Hamiltonian, you have to assume that the constraint commutes with the Hamiltonian. That means you have a closed algebra with the Hamiltonian. So you will need to add here this condition plus the alpha with the Hamiltonian. You have to be some function. Let's see, alpha, gamma, phi gamma. So some function. If this is true, then exactly the same calculation, you will pick up again a Poisson bracket with a constraint with the Hamiltonian, and then you use the algebra, and then the only difference that you will pick up one extra term here for the transformation of and then you can also add second class constraints, and then again, assuming that the constraint phi alpha, the definition of a first class constraint is that it commutes with itself, it commutes with the non-zero Hamiltonian, it commutes with the second class constraints, either any. And the calculation is a little bit longer in each case, but it's exactly the same. When you have to, this bit would be always the same. There will be no changes at all in this part. This one you leave it just like this, and this one becomes a bit more complicated, a bit longer, with the different ingredients if you add more ingredients, but it's exactly the same. And then you're covering, in one calculation, you're covering the gauge variance of a huge number of systems. So, gravity, just to finish this part, so just to make a point, the square root of g, and you can add lambda if you want to, then this can be written as pi j, j by j minus 2 constraints. Well, these are Lagrange multipliers, and h and hi are functions of pi's and j's, which commute. They have a closed algebra, and this algebra is not exactly the diffeomorphism algebra. There's some subtle details, but it's a closed algebra, which is important. It's a closed algebra. So this calculation over here, anyway, is included that problem. If you have a Yang-Mills theory, this is quite fun to do. So I will talk about Yang-Mills in general. If it is abelian, then you down to Maxwell theorem. You will have the whole thing. Basically, p squared by. I'm not very careful with some details, but the idea is this is our derivative in y. So if you have a Yang-Mills action, there's a gauge field, which is a space-time gauge field that carries a Lie algebra index. So the time component of the gauge field will be the Lagrange multiplier. And the space component, so this is split as 0 ki. So the time component is a Lagrange multiplier, and the spatial components are the canonical variables. And they have a canonical momentum, and then there's a non-zero Hamiltonian. In this case, this will be H0. And what is quite fun to do is that, and it's actually a very easy calculation. So this is the constraint that carries now the algebra index, And then it's a beautiful calculation. It's quite nice to do it. The constraint algebra is exactly the Lie algebra. So these theories assume a Lie algebra, and the Lie algebra have some structure constants, which are sitting in the algebra, and the constraint algebra satisfies exactly the correct algebra. And they compute also with the Hamiltonian. Here, I don't remember now what the alpha. There's something times 5, but yeah, I don't remember the coefficient here. Actually, the one is 0, exactly 0. Yeah, this is exactly 0, so that's exactly 0. Because the Hamiltonian doesn't carry an index, so the algebra index. There's a trace here outside. So the Hamiltonian doesn't have a algebra index, so this is exactly 0. So then it's very easy to do the calculation again, and then you can work out all the consequences. Okay, so Chern-Simons will be the last example, which is quite popular in Chile. Again, the Chern-Simons theory has it's a space-time vector difference. I mean, kinematics is the same as the Yang-Mills theory. So it's not exactly the same, but the dynamics is different. So the fields are the same, but the action is different. So this is the famous Chern-Simons action in 3 dimensions. And then you can prove again that the time component is a Lagrange multiplier for a constraint, and the space components can form this canonical coordinates. In this case, you don't need an extra momenta. A is conjugate with itself. Okay, you name it any gauge theory, your favorite gauge theory, and I will give you the Hamiltonian version with some constraint that satisfy the constraint. And that's it. So you can, with this calculation, you're covering a huge number of systems. It's quite fun to work out. We did it with Mark Renaud a long time ago, to work out the dynamics in the 5-dimensional Chern-Simons theories. The 5-dimensional are more complicated, and it's a beautiful calculation to work out the whole Hamiltonian version. Okay, any questions? I'm going now to change subject. No?
And the quantization.
Either very clear or
can you quantize from here? Can you quantize from here?
Well, okay, so there's
usually some problem with general relativity, I assume.
So, in principle, what would you do? When you quantize, and there's actually a very nice calculation. So this was all done by Dirac, and then he proposed what is called the Dirac quantization. And his idea is that the constraints has to eliminate the wave function. So this is the D equation. So you transform. So the basic point is to transform the P's and Q's into operators. Then you say that they have no zero commutation relation, which will be P with Q equal I H bar. That's the usual thing. So then now this becomes an operator. This is a Hamilton, and then you say this will act on the wave function, and it has to be equal to 0 because the wave function has to be H invariant. This is the generator of the transformation. This is what we just proved. By the way, this is normally the sentence associated to this is like saying that the constraint generates the gauge transformations. So it's implement the gauge transformations on the lattice Q, P, and lambda. So then Dirac had the idea that the quantization of a gauge theory amounts to solve that equation. There's a very beautiful one. If I can remember quickly, you can take the free particle. This is a very nice calculation. Take a free particle with some potential. This is a good exercise. And then what you do is you transform time into a canonical variable. This is a trick. You will understand why I'm doing this in 1 second. This action can be written this way. The lambda, the lambda times, and I will write here the q of the lambda, sorry, the q of the lambda times the lambda of the t, so minus d of lambda. So I've done nothing really. I've done absolutely nothing. This one cancels that one, this is the t, and this one cancels that one over there, so I just introduced a parameter. But the crucial step is to treat this now as an action q of lambda and t of lambda. So this is, you can take the inverse, so this is the derivative of t with respect to lambda, 1 over that one. And then you can consider this as an action for two variables. When you do that, then you have a GH invariance. And the reason you have a GH invariance is that lambda can be anything you want. So this is an action which has a one-dimensional diffeomorphism invariance. Because obviously, the way I introduce lambda is completely trivial. So obviously, lambda can be anything. Okay? So it's a bit of a calculation, but you can see that intuitively, it's quite clear that this action will have a GH invariance. Because it has a GH invariance, it has a constraint. And the constraint, I can write it out, if I remember, the constraint is p squared divided to m. The dt now is dt is the minus sign probably, and so now you have this action, and then you work out the Hamiltonian formulation. So that means you take the radiation with respect to the velocity, the q of the lambda, and that you call it p, and the momentum associated to time, you call it pt, which is the momentum associated to this variable. This is the velocity. This is the t of the lambda. Where t is a function of lambda. So you treat it like t dot. It's a velocity. So you have to define the momentum for it. You define momentum and you call it pt. Well, the constraint happens to be this combination, and then when you implement the Dirac condensation condition, what you get is exactly Schrödinger equation, because this becomes the dt, and this is the Laplacian, and this is the potential. So you get exactly the equation of motion of quantum mechanics. That remains to be filled, but this is a beautiful calculation. So quantization. I think I would say if we knew how to quantize gravity already, okay, let me put it this way. This equation has so many problems. It's a really complicated equation, and nobody has ever managed to really understand it properly. Not even solve it, just understand what it means. I mentioned yesterday a paper by Witten, which is a 2022, I think it's just 1 or 2 years ago. Witten was trying to solve this equation, exactly this equation, something that you can find on the web. And then the idea for gravity. So he writes the constraints of gravity and then trying to make sense of this equation. Using Van invariance, and he used a lot of tricks and a lot of math. Is of course, there's a bit of heavy math, but he tried to understand this. So this equation, this way of quantizing gravity has not been successful. It has to be said, has not been successful. On the other hand, the other methods, string theory, for example, I would say far more successful. I mean, it has far more ideas, but nobody would say that it's already settled. It's far from settled. So I think people are coming back to this equation, maybe with fresh ideas, which is probably how Witten felt, maybe after so many years, and maybe I think it's an open thing. This is, I have to be honest, there are many problems here, technical problems, but it doesn't mean that it's definitely not wrong. This example here, for example, the way you can derive Schrödinger equation is actually remarkable. You just work it out from a three-particle Lagrangian, or sorry, not three. It's a particle Lagrangian on a given potential, and then you just introduce a parameter. Then follow the procedure. You find the gauge imbalance, then you go to the desired quantization, and you get exactly the Schrödinger equation is remarkable. So I think we need to keep this alive. You are young people, you need to learn it, you need to how to work out with this. And then one day, things will be understood in a better way. So, okay, I want to move now into something different, which will use properties of the Lagrangian. As I said, there are some things which are wonderful in the Hamiltonian, and then some others are wonderful in the Lagrangian. Remember the sentence I said yesterday? This calculation in the Lagrangian it just cannot be done. You cannot parametrize. We are parametrizing all gauge theories in this way. All gauge theories fall in this class, and this is the calculation for all gauge theories. So you can parametrize all gauge theories. You give me the structure constant, give me the constraint, the constant, and well, here you are. In the Lagrangian, you cannot do that. Yeah. Okay, now I'm going to show you something which is very beautiful using the Lagrangian. The Lagrangian equations. Just to make the point that they're both important. So far we talked a lot about constraints, the role of constraints, which are equal to zero. At the end of the day, constraints contribute to the equation of motion, of course, but at the end of the day, the values are equal to zero. Now I want to talk about infinity, things which are divergent, and how we can make sense of them in a pretty general way, using the Lagrangian. So somehow what I'm trying to exhibit here is that there's some things which can be collected. You can have a global view. Like gauge theory, you can have a global view if you understand them in the Hamiltonian formulation. The idea of a constraint has certain properties. That's includes all gauge theory. Now I'm going to show you that there's a general way to understand some kind of divergences. Divergences, there are two types of divergences in field theory. There's ultraviolet ones and infrared ones. I'm going to show you how to deal with infrared divergences. However, in the ADS-CFT context, an infrared divergence corresponds to an ultraviolet one in the CFT. So actually what I'm going to tell you now, how to deal with infrared divergences, will be quite relevant to understand ultraviolet divergences in a conformal field theory. So, this is what the motivation is this one. This famous idea that Feynman introduced. Let's talk about, let me put a plus sign here. The idea that you want to compute, well, all scattering matrices, etc. So many things you want to compute in quantum mechanics, and they can all be collected in this concept that you take the functional integral with some initial conditions, or initial and final condition, for example, and then you do the integral over all fields, and that will give you the amplitude from one state to another state. Now, it became immediately clear that actually that was the motivation. I mean, Feynman knew that he had to make sense of this approximation of the classical action, because in principle, or one should expect, that this huge integral is dominated by the classical configuration. So this should be an approximation that you have to be able to make sense of it. Actually, the historian, I'm not sure whether this is true or not, but Dirac was the first one to point out that the amplitude of a given process should be approximated to some extent by the classical action going from one event to the other event. And he wrote this formula. He knew that the amplitude from going from A to B should be more or less the classical action going from A to B. But he knew also that that was an approximation. There wasn't a solution to equations. And then finally I pointed out that to transform that into an equality, what you have to do is to integrate over all fields in between. It's a huge process, of course. The history says that Feynman went to see Dirac once, and he was very happy. You know, you were completely correct, and the right way to do it, or the way to get the right result, the exact result, is to make the integral over all paths, which is a path integral, something completely unknown. Apparently, Dirac looked at him and said, "Isn't it obvious?" That was his comment. Anyway, okay, so we want to make sense of this, but of course, this classical action will be an integral over t, typically, over some x over Lagrangian, and then this almost always diverges. Let's say, in an open space. If you're in a compact space, of course, it will not diverge, but if you're in an open space, ADS, for example, a flat space, even flat space, this will diverge. And these are called typically infrared divergences because they happen when you're integrating over a large volume, and then if the fields don't fall fast enough, then this will diverge. This is typically when you have massless fields. If you have massive fields, they decay very quickly, and you won't have divergences. But gauge theories are exactly the case where you have massless fields, like in gravity, for example, and then you pick up divergences. So what I want to show you is, as we did for gauge theories, it's a general framework for gauge theories. I want to show you a general way to deal with these divergences, and then look at some examples. So I just want to remember. Okay, so I will mix up this problem with the divergences with another problem. So typically, we write the action, which would be some Lagrangian plus this mysterious boundary term. And then we all know that with great work, a lot of work, we have to go through some argument and to come up with what is the boundary term, the right boundary term. Now, I want to separate this boundary term in two things. One is cancel divergences, and the other one is having the right boundary conditions. These two things often get mixed up. And in fact, there are many calculations. For example, Gibbons and Hawking, who were the first one who did the calculation for the black hole entropy using the path integral, they write a boundary term for the action, which is called the Gibbons-Hawking boundary term. And via mysterious subtraction, they subtract the value of the boundary term on flat space. Then they get something here which will give the right result. Okay? But if you do the calculation carefully, you will see that this boundary term does two things. One is that it subtracted divergence because the action is invariant, and then the boundary term will cancel the divergence, but at the same time, together with it, it brings a finite piece, and that gives you the right entropy. And it's quite subtle. If you read the paper, you can get really confused because it's a very subtle calculation, and they don't give a lot of details. In a way, I think it works, and let's just leave it as it is. So what I want to do is to separate these two things and then treat them differently. One problem is to make sure that the action is finite. When I do the integral, I will get some boundary terms here, which will be divergent, such that they will cancel the divergences coming from here. But on the other hand, I need terms which have to do with boundary conditions. And what do I mean by that? Has to do with the functional integral. Let me be, for 1 second, let's go back to the particle case. This is the easiest way to, this is something we do every time you find the only Lagrange equations for a problem, what you say is that in time Q1, the system has position Q1, and then so you have from Q1 to Q2, and then you compare different histories with those 2 points fixed, and that gives you the extremum of the action. And then Q1 and Q2 are fixed at the time T1 at the time T2. And this will give you the propagate the amplitude going to Q1 to Q2. So on the one hand, you do this picture when you are computing all the Lagrange equations, and then you fix this one and fix that one. Or when you're computing the amplitude, the quantum amplitude from going from Q1 to Q2, you will do the full integral of all path with this point and that point fixed. And that's very important. And the reason is that one way to see the variation of the action will be, what here would be delta Q divided by delta 1 So this is when you compute the variation of the action, you give the equation of motion plus the boundary term, and then you impose the condition that delta Q at T1 is equal to 0, and delta Q at T2 is also equal to 0. Only if those conditions are imposed, then this is 0, because this is evaluated at these 2 times, this is 0, and then the variation of the action gives you the equation of motion, and then if the equation of motion are valid, then the action has an extremum. If these conditions are not imposed, or if the boundary term is different, well, there will be a problem. So, if the boundary term is this one, then these boundary conditions are correct. And you need to make sure that the boundary term will be synchronized with your boundary conditions, such that the equation of motion really gives you an extremum of the action. And this is the action. Once you have done that classical calculation, you make sure that the classical calculation is correct. Then you plug it into the functional integral, and then you compute the amplitude from going to Q1 to Q2, which are these 2 fixed points. And then, in one case, in the classical, you compare different trajectories. In the quantum version, you sum over all trajectories, but always with these 2 points fixed. So that in this sense, the classical and quantum calculation are quite related. Okay, so cancel the boundary term will cancel divergences. That's one rule of the boundary term. Another rule is to make sure that you have the right boundary conditions. Okay, so with this motivation, let's look at some example. So, for example, you have a field theory example.
Professor, sorry, you define K in the whiteboard,
yes.
Blackboard, but where is K1 and K2 in the action?
In the
functional integral minus for the 2 different place are?
This is the action. This action will carry some boundary term, okay? This boundary term has to be such that the variation of the action is the equation of motion plus something which is 0 when Q1 and Q2 are fixed.
Okay.
They're not implicitly inside the action. But you build up the boundary. I will show you examples. You build the boundary term such that the action has an extremum with those boundary conditions. So they're somehow implicitly inside. It's a very good question. Let's go through examples and then we will get clear. So for example, if you have a scalar field, because I will be talking now about the radial boundary, not really the time boundary. So you have for example, on ABS, okay? This is a very famous case. Sorry. No, some math. So I have a scalar field. Well, the signs are relevant here. Okay, so the solutions. This is when R goes to infinity. Okay? So it will be R to some power. I'm going to put this by 0. Yes. I will clarify the notation in 1 second. Okay, so my idea now is that I will be working on the Euclidean. This will only be done in the Euclidean formalism because it's easier. There's some fundamental difference with the Minkowski one, but let me be in the easiest case. So in the Euclidean formulation, the idea is to consider the space-time like as a ball, where I have a radial coordinate going from r equals 0 to r equal infinity, and then this the ball I will parameterize it with some coordinates xi, and the time is inside here. Time is inside the coordinate, this transverse coordinate. So I have the radial coordinate going from some value here to infinity, and then I have transverse coordinates which run in this direction. Okay, these are the xi, and the xi, as I said, include time. So this will be time and two angles, for example. In 4 dimensions, it will be time, theta and phi, and then r running outside. And this is the topology of this problem. So typically, if you have a scalar field with some mass m, there will be an initial equation that has to do with the mass. I don't want to go into these details, but then this is a Frobenius problem. You have two solutions to the initial equation. There will be some sigma 1, sigma 2. Typically, sigma 1 and sigma 2 can be positive. In good cases, one of them will be negative, but the other one definitely will be positive. And then if there's a positive one, this field diverges when R goes to infinity. So what is called normally the normalizable mode is that you just say, I put all this, I choose conditions such that they're all 0, and I just stick to this solution, which in principle is regular. But experience with the ADS-CFT has shown that it's actually very useful to keep the whole thing, keep the whole solution, and then subtract the infinities, and then work out the action with a subtraction term, which can be made finite. So the variation here, the variation of the action is the rate of motion plus we will pick up. I will write it in general for any Lagrangian. This is the R, and this is the variation phi integrated over all the XR. This is the boundary. The boundary here has a normal, which is in the radial direction. So then you use Stokes' theorem, and then the only thing you will pick up is the variation of the Lagrangian with respect to the radial derivative of the field. That will be the boundary term, and this is, of course, this is an integral over the boundary at r equal infinity. So this is what I want to make sense. I want to check whether this is finite, is infinite, and if it is divergent, what do I do with it? Okay, so I have here the field, because the Lagrangian depends on the field, but I also have the fluctuation, delta, the variation of the field. So let's formulate the problem this way. The field, I will assume that very, very far away, the field will have this form. For some coefficients, phi 0, phi 1, phi 2, psi 0, psi 1, psi 2. Then nothing has to be said yet with these coefficients. I just say, and you can work out the equation of motion, and then you will realize that the solution indeed had this form. Okay? So you can assume safely that very, very, very far away, the field will have the solution. So together with this, I will say that the variation of the field, very, very far away, will have exactly the same form, sigma 1, but with variations. 0. Etc. Plus. Where, just like for netted theorem, these are new functions. I'm not saying there's no relation between this one and that one. Sorry, between this one and that one. There's no relation at all. This is the field, and this is the variation of the field. I'm just saying that the fluctuations or the variation of the field will have the same form as the field itself, but with new functions, deltas, delta phi, delta psi. These are the two. By the way, this is a second order set of equations, the equation of motion of second order. So we do have two series. So one series is the series starting with sigma 1, and the other one starting with sigma 2. So you have this is like the seed of the series, the seed of that one, and then normally if you plug into the equation of motion, then you will find that phi 1 gets related to phi 2 gets related to phi 1, and phi 0, sorry, and then you build a solution. So given this and given that, you can build a solution. This is the statement. Okay, but now what we want to make sense is to say, well.
Sorry, you skipped the variation over R because we're on the boundary, right? And we have fixed
Okay,
the.
so, okay, let's start again. So this is the topology of my problem. Okay? So I have this is not very well. Let me the same. This is the topology of my problem. So when I vary the action, I will pick a boundary term. The boundary is this sphere, we call it SD, at infinity. Okay? So this is where I will pick up a boundary term, which is located at R very, very far away, and it's an integral over the transverse directions.
Okay, but when
Okay.
you did the variation of B in the second line
Then-
there, you
so
skipped the variation of the R term.
I'm saying that around here, very, very, very far away, the field will behave in this way, but in the boundary domain, I don't only have the field, I also have delta, the relation with the field.
Yes.
So what I'm saying is that if the field behaves in this way, the variation of the field will behave exactly the same way, but with different coefficients.
Okay. And you didn't vary over.
And that makes sense because the fluctuations normally are also solution to the equation of motion.
Okay.
So it's not something, what is man doing? You know, it makes a lot of sense. What I want to stress is that, again, like in netted theorem, I write here phi naught, and then here delta phi naught, but this is one function, this is another function. There's no relation between them. This is just completely arbitrary functions. Okay, so what is the problem? We have two problems. We have the equation of motion, and we have a boundary term. So this boundary term, we need to make sure two things. First, we should define it. I don't want a divergent boundary term. The variation of the action has one part which is equal to 0, but then I have this other combination there, and I want this to be finite. This will not be the case if I just take this action. It's not necessarily the case, and it's not the case. What I would like to happen is that there might exist some boundary term which I can add to the action such that when I take this variation, then I will include here plus the variation of B, and this one will cancel divergences coming from there. This is what I would like to be able to prove. I want to prove that I can add a boundary term here such that this is finite. Now, here comes the crucial point. You can look at this problem in two different ways. One way, if you just consider the action and the addition of a boundary term, and then look at that problem, and then you say, and then you never worry about the variations. You just say, I have this field, I know the field will behave in this way, I plug it here, and I try to find a boundary term B, which would be a sort of counter term, such that that plus that is finite. That's one way to look at the problem. The other way to look at the problem, which is will give you a general view of the solution to the problem, is not to look at the action, but to look at the variation of the action. So let's look at let's not try to make the action finite first. Let's try to make the variation of the action finite. Okay, which is this problem here. The variation will give you the equation motion plus this boundary term, and then I wonder whether I can add a boundary term such that the variation is finite. I will argue at the end. I will argue two things. If you look at this problem, that problem. If you look at this problem, you can do. It's extremely complicated, and people have done it case by case. So you do it for the scalar field, you do it for Maxwell field, for vector fields, for small field. You have to go machine. There's an algorithm, but you have to go through to check that the algorithm is working case by case. If you look at this other problem, which is only making sure that the variation of the action is finite, we will be able to make a general statement that basically that these different divergences can always be removed, always for any system. Okay, let's make that true. But secondly, the boundary term has another problem, which is still there. So on the left, cancel divergences. But then on the other hand, I also want the boundary term to provide me with the right boundary conditions. So in this case here, typically, you might say, I want to define this problem in which this function here is fixed. So this is the function that I will regard as like the Q1. This is the function that I will fix. Remember when you solved the Laplace equation with that horrible brute Jackson, and then you have the problem finding the potential with some given boundary condition. So you give, for example, V on one half and minus V on the other half, and then you want to find the potential with this boundary condition. So this is the classic problem of the Laplace equation, and this extends in this case. So this is the dominant field, the dominant part, because sigma 1 is the one which is going up. This is sigma 1 is greater than sigma 2. So this is the dominant part, and I will say, I want this action to be stationary when this field is fixed. Okay? So what I would like to happen is that whatever this is, when I compute it, I will have to make a lot of calculations. I would like this to be the variation of something times the variation of that person. And nothing else. And that's something, hopefully, will be finite. So we're dealing with two different things. One is the infinity problem, and second, the variation problem. So if I want this boundary condition, this is, by the way, this is like the field at infinity. This is the value up to this growing coefficient. This is like the field at infinity. This is the one which I want to fix. So I want to make sure that the variation of the action gives me something which I need to compute, maybe who knows what, times the variation of that particular combination. Okay? If that is true, then if I fix this, then this is 0, and the action is stationary, the equation of motion. Okay? So we want to deal with these two things in one go. Is that clear what the program is? So I will leave that. So the boundary term has two roles. Killing divergences and making sure that you have the right variation such that the action will be trivial when your favorite boundary condition is applied. Okay, so let's look at this. Let's look at this object here. This is where everything is. This is the object that I need to study. I need to understand the values of this object. So the Lagrangian depends on the field phi, and the field, I am assuming it has this expression. Of course, I wrote this for the scalar field, but the comments I'm going to make will be valid for any field at all. I mean, there's nothing in particular with this behavior. Okay? There can be logarithms, there can be anything. I'm just saying that there will be some asymptotic series. Some asymptotic series of some equation of motion. So this coefficient depends on phi, and then there will be the variation of the field, which I am assuming that the variation satisfies also, the fluctuation satisfies also the equation of motion. So I want to evaluate this. So the trick I'm going to do is that I want to separate the problem of divergences with the problem of boundary conditions, because dealing with both problems in one go is actually complicated. So I want to separate them, and the way I will do is a trick. I will take the greater derivative of this. Why do I do this? Because in a way, I want to leave aside the boundary conditions, which is the constant part. So this, let me, before I take the derivative, this is some of this which is divergent, a function of r which is divergent, at least which is finite, plus this which is convergent. So when I compute this, I plug the field phi and I plug the variation of the field. This is the field, for this example, this is the field, this is the variation. I plug it in, and I will pick up terms which blow up when r goes to infinity, terms which are finite, and things which are convergent. 1 over r, 1 over r squared, etc. Okay? So, of course, this ones, I don't need to even look at them, they will disappear. The important ones are this one and that one. So I want to separate the problem. I say, well, let's look at this one first, and then we'll look at those ones. So to do that, what I will do, I will take the greater derivative of this. If I take the greater derivative, I will pick up a prime here, and this one will disappear. Let's look at this problem first. Okay, so if we do that, there's a short calculation here. We will do it. Right, that uses the backward anyway. Let me, what I will do is run it again. We can leave it over. So this is a quick calculation. The Euler so the Euler equation for these problems are the following. Here they are. Phi prime plus d I down equals minus. These are the equation, the Euler equation which I have split. Normally you would write it like this. With the space-time index, and I split it up into the radial part and the orthogonal to the radial part. Okay. So what I see is what I will do, and this is exactly the piece which is entering here. So I will replace the Euler equation here, and I hope I have it on this page. Probably not. Okay, this will give me. There's a much shorter way to do this, I will tell you later, but this is I think, more clear way to do the calculation. Minus. I'm missing something here. Okay, let's proceed and hopefully it will be correct. I'm missing, somebody tells me I'm missing something here. I didn't do wrong. 1 second. I will mine and then 1 second. It's an increment. Okay, no, that's good. Yeah. It's correct. I will continue here. I will do an integral by parts. And then I take this derivative and then I pass it to the other side. So I will pick up a plus sign. Minus something. Yeah, just the last step I needed. There's a minus sign here. And there's a derivative acting on this piece. So I pass the derivative to this piece and then plus a boundary term. A boundary term on the transverse coordinate. This will disappear because I'm integrating. This is all integrated and this is closed. So this sphere is T, which has no boundary. So that boundary term will disappear. I don't need to look at this. And then this is exactly the variation of the Lagrange. Because it's the variation with respect to phi times the phi, the variation with respect to phi prime times the variation with phi prime, the variation with respect to phi I, the variation of phi I. This is exactly the variation of them. Okay, so what's this is a very important result. What this is telling me is that the radial derivative of this term, which contains all divergences, is integrable. It can be written as the variation of something. And if it can be written as the variation of something, I can always put this something here, and the divergences will disappear. I put it with a minus sign, of course. This is actually not a trivial statement, because I have here things depending on phi, and things depending on delta phi. But I won't be able to make the action finite adding variation of the field. The variation of the field is something I understand at the level of the equation of motion, but I don't understand it at the level of the action. I need to be able to prove that there exists a counter term which will cancel the pieces which diverge. So what did I do? I look at the pieces that, first I look at the variation of the action. I look at the pieces that might diverge, because I took the derivative here. So I pick up only the pieces which depends on now. And then I do this calculation. I prove that this can be written as the variation of something. This is not the variation of anything. This might not be a local function of the field. I need to make sure that this is a local function of the field. But this calculation shows me that this is integral. This is the variation of something. And therefore, always, for any theory, this is any theory that descends from the Lagrange. By the way, you can add higher derivatives if you want to. You can consider Lagrange with second derivatives, third derivatives, whatever, and then the calculation goes exactly the same way. You can only get rid of the divergences, always. So that means that your favorite action, until this now, you have your whatever action you started with, then you can always add something I will call it B infinity, such that this is that B always exists. Then I don't need to compute it. In fact, I don't need, because the action I want is this one. This is the final one. I don't need to even look at the divergences. And I will prove to you that, I'm not sure if I will have time to do it now. I will show you the examples, and then we can work them out next class, the next session. I can compute now the final action without ever even compute them, these divergent pieces. I just need to know that it exists, counter them, that will cancel them. Once I've done that, I can compute, I can concentrate on the final part, and that will give me all the information I need. So we will do the following examples, and I'll do them next week. I'm sorry, next session. This can be applied in, for example, in black hole. Basically, in that case, the action is, the starting action is the square root of R, or you can add a lambda. When you are constant, this is, the calculation is almost exactly the same, with one, with lambda, without lambda, there's no difference. So you start, this is the starting action, this, let me call it A0. You start with that action. Then you take the variation of the action, which will give you, of course, the equation of motion, plus something. There will be divergences in the boundary term. You don't look at them, you know that you can subtract them. The next step is that to decide what the boundary conditions are. And normally for black hole physics, what you do is that you have some asymptotic region, and then you have a period here, which is the Euclidean period, called beta. Beta is the inverse temperature, and then you want beta to be fixed. So the only thing you need to make sure is that the variation of the action has to be something times delta beta. And that something will be the mass, actually minus the mass. Okay? And then that is also a very quick way to compute the mass of the black hole, to make sure that n, the coefficient that is in the Schwarzschild solution, is the mass of the black hole. This is one way to do that calculation. So the key simplification here is that there will be a boundary term, which I call it B infinity, plus another boundary term, which I will call B variational. One boundary term, get rid of singularities. I know it exists, so that I don't need to compute it. And then I focus on the final piece. I just throw away all the divergences, and I focus on the final piece. And on the final piece, I make sure then I will need to add other boundary terms which are finite, such that the variation of the action is something times delta beta, because beta is what I want to kind of fix in black hole physics. You have a given temperature, and the black hole has a fixed temperature.
What is beta?
Sorry?
What is beta?
Right?
What is
Beta is the Euclidean period.
Is a coordinate?
Yeah. In fact, yeah, it's not the coordinate, it's the period of the coordinate. So normally in Schwarzschild, you write it like this. P square. So if I fix this running from 0 to 1, the coordinate, I just decide t goes from 0 to 1, then this constant here is the period of this coordinate. And this is what you identify with the inverse temperature.
It is part of the metric. Yeah. Beta is the metric, part of the metric.
The metric, yeah, enters exactly. The metric, sorry, I heard the measure. Yeah, it enters inside the metric, yes.
Yes.
So then you can, doing this calculation, you will be able to find what is the mass of a black hole, and second, what is the entropy. Because, of course, you will associate this with the free energy for a given matter. So we will do that calculation next week, next session, yes.
The final part of the boundary terms will also apport to the final part of the fin action? Or
Sorry. Because here, yeah, let me add here within equals. So that the final, at the end of the day, you add divergent pieces, which cancel divergences here, but then you will have to add also, not necessarily, but you have to look at, you have to make sure that as I said here, you have to make sure that the finite, okay, let me, this is the initial action. Let me use the same notation. This is the final action. So first step, you subtract the divergences. But that, you don't have to look at them, because you know they can be subtracted. Then you look at you pick up the finite pieces, and the finite pieces you will need to add other terms such that the variation of the finite piece is something times delta beta. That means that if delta beta is 0, then the action has an equilibrium. Okay, and then you will need to add another boundary term. And after you've done that, this bit here, through regularity, well, you have to make sure this is pretty much set for some regularity condition. This will depend on beta, and then all the thermodynamic information will flow in a very simple way. And you never have to look at the divergent pieces. You just don't look at them. It's not necessary.
But we also have to compute the finite part of the boundary term.
I will. This, I know it exists. I don't look at it. And this one I will compute it explicitly. And the other example, which I can work out, is the calculation of correlators in ADS-CFT. This is more or less, well, the easiest example is the scalar field. We have done it with electric and really complicated systems. And you do exactly the same. You can throw away the divergences, and then making sure that the action has an equilibrium in the right boundary condition gives you the correct correlator, which is a very subtle calculation. If you did it, so the key difference with many of the literature that you would find is to focus on the variation of the action, not to focus on the action. And I would argue that you're not losing anything. So if you just say, this is my action, and I want to make sure this action is finite, it's actually a really complicated function. It's very complicated. If you look at the variation of the action, and then you make sure that the variation is finite, you get two things. First, all divergent pieces, you know that they can be subtracted. Second, you get explicitly the problem, the variation problem, which is what is the boundary condition and what is the right boundary term for given my boundary condition. It's built in the calculation because you're looking at the variation of the action. The variation of the action is what gives you the relationship between boundary terms and the extreme of the action. If you don't look at the variation of the action, you will never discover that relationship. So that's why looking at the variation is actually a very, very easy way to do the calculations. And I will also argue that even when you're doing the full path integral, actually, funnily enough, when you compute the full path integral, normally you compute it as a function of some current, and at the end of the day, you also take variations with respect to the current because you want to compute correlation functions. And the correlation functions are given by derivatives or the functional integral, and again, you're dealing with variations of the action. It's quite funny that the same principle can be applied to the full calculation, even the full quantity calculation. And I will be talking about that as a family integration. Okay, I think there's some time for questions. So next session will be a bit of black hole thermodynamics. I will work out with all details the Schwarzschild case, and then I will compute a correlator, ADS-CFT correlator using these ideas.
So there is a question because one boundary conditions, one boundary term, I represented by those method, but another boundary term, I example.
So that's something that
the another boundary term, I don't know. Let's see, because the regularization boundary term, I'm going to see like those names, for example, but the another boundary term, is exactly the other boundary concept be sort of big.
I think he's regarding about the BD, the last.
Yes.
Because you have I 0.
Yes. But what is the question? I understand. What is the problem?
The question is, what's this boundary in terms?
Okay, very quickly, in the black hole case, if you start with this action, what you get, when you consider the evaluation of the action, of course you get the equation of motion, and then you subtract the vertices, actually that bit is, in this case, is triggered, and then what you get is, so let me say that, I will say that G00 will go like 1 plus some point by R.
Okay, the boundary of the fields that.
Well, I need to assume some boundary condition for my fields. Okay. So, for example, G naught will be some relation which is I pick up from the Schwarzschild matrix. Okay. Once I do that, I will compute the variation. I mean, here, what I will discover is that I will pick up a term which has the variation of this guy. Okay. And then beta will be inside here. But that's not what I want, because I don't want to fix, it's obviously, this coefficient is related to the mass, I know that. I don't want to fix the mass, I want to fix the temperature. Okay? So then what I will do is that I subtract beta times F1 from here, beta times F1, and the variation of that will give you something which is F1 times the variation of beta. This is just a like Legendre transform. And then what I achieve is that if beta is fixed, then the variation of the action is 0. Of course, you can do the microcanonical ensemble, which the mass is fixed, but that's actually a bit more boring in this case. It's more interesting to do the canonical ensemble where the temperature is fixed. So that's what I what is written here. One part is make sure that you cancel the divergences, and the second part is making sure you have the right boundary conditions. So you decide what is fixed at the boundary. This is you're right. As an experimentalist, you say this is what is fixed. So if you make an experiment, you say I fix the temperature. There's a boat here with particles, but I make sure this is a fixed temperature, and the particles will adjust the pressure. Many other variables they can move freely, such that the temperature is given. So the action for that problem, you want to make sure that the variation of the action will be something times delta beta. If beta is fixed, then the variation of the action is 0. Just like exactly same like this in a it's the same principle as in a particle. When you compute the only Lagrange equations going from one point to one to another point to two, where these 2 points are fixed. The reason they're fixed is because the boundary terms is the relation will delta Q evaluated at T1, T2. So you want to make sure that if this is fixed at T1 and T2, then the boundary term will be 0, and the action has an effect. It's the same principle.